Hey, so in this video, I'll be explaining assignment 2 for my artificial intelligence programming class. I'll start by demoing the GUI so you can have a good idea of what's going on, and then I will walk through the code. So this is what the GUI looks like on startup. We can ask it to solve one puzzle, and it'll start in a random configuration. We can click it multiple times, and you can see it'll start in random spots. We have two buttons, forward and back. This allows us to iterate step by step through the puzzle solution. So this is our start state, and we can click through. And as we can see in the terminal, this will take approximately 22 steps to solve. Not approximately, exactly 22. So this is, as you can see, our solution state. And the second half is for generating the statistics asked. So we're using the A-star algorithm. We're solving 10 puzzles. The average number of nodes visited happens to be 350 in this case, and the average runtime is 24 milliseconds. The heuristic we're using is the Manhattan distance. So that's the GUI. Now to talk about the code. So in our function, we have our header. Not program, we have our header. We are importing our dependencies. This we're making a class. This is one of the two classes we have in the program. This class represents a puzzle node. Node being just one of the points inside the A-star algorithm tree. So one node just represents one state of the problem, one configuration of the numbers. Parent represents if there were any nodes before it. Action represents the action it's about to take. Cost is the cost we're at. The heuristic is just the value from the Manhattan distance. And the priority is the cost plus the heuristic. This underscore underscore LT stands is a dunder method. We're overriding the less than function. So when we use our heap later on in the solve problem function, we can order our nodes by priority using the less than function. So this is the Manhattan distance function. It'll take in the current state and the goal state, and it'll calculate uh, the distance. So it'll look at all the tiles that are not zero, and it'll look at where they're supposed to be in the goal state, and it'll calculate the absolute distance with row and column. If you're seeing this, don't get confused. This does not mean divide. This is just Python convention for uh, extending the line. This is the same thing as having everything on the same line, like this. But with PEP8 formatting style guidelines, you do this because you don't want the lines to be too long. The next function, get possible actions. So this will take in the current states, and it'll check what actions are possible. So if your zero tile is at the top of the puzzle, you cannot move up. If your tile is at the bottom, you can't move down. So if you're all the way to the left, you can't move left, and if you're all the way to the right, you can't go further right. And it'll just return that list of all the possible actions. Apply actions will take in the current state and the action you want to apply and just swap the tile. So it'll swap the zero tile with whichever action it happened to pick. Get opposite action. This is a function we use for the generating a solvable puzzle, but basically it just returns the opposite action. So if you input up, it'll return down. Reconstruct path. So this will take in a child node and work its way up to find the very topmost parent node and construct a list. That's the path. All the way from the beginning to end. This is how we have our path history, basically. Um, Generate solvable start state. The reason I included this is because sometimes when you just generate a random 3x3 array, it might not be solvable, and that was messing with some of the program reliability. So I take the goal state, I pass in the goal state, and I pass in the number of moves, random moves I want it to make. So it'll generate some possible actions. It'll ensure that the next action is not the exact opposite of the previous action because we don't want it to undo any of the randomness progress that it's been making. And it will just generate a new puzzle for the system to solve, for the algorithm to solve. Solve puzzle function. So this will take in a goal, a start state, and a goal state, and it'll use the A star algorithm to return a constructed path as well as the number of nodes visited. So the way it works is it'll create the start node, which is just an object of the puzzle class we mentioned at the top of the document. It takes in the start state that we pass in. Uh, no parent because it's the start node. No action because it's the start node. And obviously the heuristic is the Manhattan distance, like we talked about earlier. This is an open list. So this list basically just holds all the nodes that are open that haven't been visited yet. Closed set. So this stores all the states that we've already looked at, so we avoid revisiting them, and that helps with convergence speed. Uh, so while the list is open, while we have nodes to explore, um, we pop from the heap. So this is our little priority queue, priority heap. It'll pop from it and then make that our current node. If we're equal to the goal state, then we return our reconstructed path and the number of nodes visited. Otherwise, we add to the closed set so we don't visit this state again. And then we get a list of possible actions. And then for every action that are possible, apply that action. So it'll apply maybe three or four actions. And then if one of those states is not in the closed state, meaning like we haven't looked at that state before, then generate a new cost, figure out the new heuristic, and create a new node using that puzzle class initialization. And then push that to the heap. So now we're adding a new node uh, ready to be taken, ready to be analyzed. So that's how, and then it'll keep going over and over and over again until the current node, here it is, current node is equal to the goal. Um, generate table. So this is a function that gets run once you click the generate function table. So it'll just run basically that same solution, that solve puzzle, just however many times you input. In our case, I inputted 10. So it'll create 10 random new start states, solve them, and sum up the total times each solution takes and the number visited. So we can calculate our average number of visited nodes and our average runtime. And then solve one puzzle. This function is used for the top part of the GUI. It just generates one start state, iterates through the problem, and returns the start state and the steps, and it prints it to the screen. Okay, so this is our second class in the program. This class is responsible for holding all the information about the GUI, the graphical user interface. It has initialization, and this function right here is for initialization of the UI. For this project, instead of making the entire UI in Python, I decided to make the UI in Python Designer and just import the .ui file. Uh, that was that makes things a little bit easier. And then I have these labels. These labels are just what we change for the numbers. And then I connect what the push buttons do. So this push button connects to this function, this push button connects to that function, so on and so forth. So this make puzzle function that gets, it'll probably make more sense if I have the GUI with me. So like I was talking about the labels, each one of these labels corresponds to a point on the grid. So when I solve one puzzle, that button is connected to this make puzzle function. So it'll create one puzzle, it'll store its state, current state, goal, and the path it took to the GUI. So then while the GUI is operating, this update labels function will just update the number for each one of the labels in the grid. This go forward will allow the solutions to step forward. And then the go back will obviously allow the solution to step back. And then the update tables functions gets called whenever I click the generate stats button. So it'll run 10 times and then output the information to the table. And then this last bit here, if name is equal to main, this is just general Python convention. It's a good practice to have. So when this file gets run, execute these commands. So create an app, create main window from the class main window, and then wait for a system exit. And that should be everything. Okay, thank you for listening.